The future of humanity is in the stars. If we wanted it badly enough, interstellar travel could be achievable in our lifetime. So what would it take to build a starship? Why don't we see evidence of galactic empires? Is our galaxy littered with the remains of single-planet civilizations, as Elon Musk has asked? Is it really so difficult to colonize other star systems? Recently, there's been some pretty wild talk of some crazy ideas for space travel technologies. We have the non-momentum conserving M drive, the wormhole from Interstellar, and the achievable warp drive. That last one is extra cool, and yeah, we'll get to it. But let me be clear. Humanity's first adventure to the stars won't and shouldn't wait for far-off fantastical technologies. Our first starship would use technologies achievable in our lifetimes. I'm being optimistic but not unrealistic. Now building a starship is going to take a huge amount of political cooperation, money and single-minded focus. Hell, this thing is so big we're going to have to assemble it in space. So for argument's sake, let's say humanity's future is at stake and we just discovered Earth 2.0 in the Alpha Centauri system. It's only 4 light-years away, but we have to get there before the Kerbals and the impending conasteroid that's on its way. So we have to focus on one design, our best chance. What do we build? The key is finding the right balance between speed of the starship and the amount of time it would take us to develop the tech to build it. No point in launching a slow ship in 20 years if the ship we launch in 50 years overtakes it. This balance is factored into something we call the weight calculation, and we want to get this right. First, option 1. Traditional rocket fuel. This is a non-starter, but just to give you an idea, the fastest manned vehicle ever was the Apollo 10 rocket, which reached a speed of nearly 25,000 miles per hour, which would get you to Alpha Centauri in nearly 120,000 years. Propellant is the big limiting challenge with space travel. Conservation of momentum sucks. To learn more, there's some very serious rocket science in this episode about farts. The rocket equation tells us that maximum speed is based on exhaust velocity, fuel mass, and spacecraft mass. If you want to get to Alpha Centauri in a human lifetime, you need to get to 10 the speed of light. And to do that with any liquid rocket fuel, you'd need a fuel tank larger than the observable universe. Not too efficient. But there are 2 ways to achieve high velocities: propel a lot of mass backwards or propel less mass at much higher speeds. Let's do the second one. We just want the fuel with maximum energy density. So direct conversion of rest mass into energy seems like the way to go. Remember, E equals mc squared. The sun does this pretty well. So let's build an engine that works like a mini-star. I'm talking option 2, fusion. In fact, why not choose the most middle option and just explode nukes behind our starship and surf the blasts? This was a real option considered for the Orion project by Freeman Dyson and others in the late 50s and 60s. We're going to assume modern thermonuclear devices and launch with roughly 3/4 of our starship's mass being taken up by 300,000 1-megaton hydrogen bombs, blast them behind us one by one over about a month, and we accelerate at 1 to around 10 of the speed of light. Nice. We get to Alpha Centauri in 44 years, assuming we don't need to slow down at the other end. Actually, slowing down is a huge issue. We need to use half of our fuel to slow down at the other end, which unfortunately means we half our speed. So let's make that 90 years for a one-way trip. This means we'd need 3 generations of humans on board that ship and pray that space babies turn out ok. Still, this tech is perhaps the most achievable in the shortest time. We already know how to build bombs. Yay, Cold War. Although the 1963 Test Ban Treaty says no space nukes, maybe we can make an exception for the future of humanity. There are also some pretty awesome options to running contained thermonuclear reactions on board. Fusion rockets, either pulse blasts like the Daedalus project, or ongoing fusion. You could push to a bit higher than Ornek this way, but probably not a lot higher. It's an awesome option and may actually happen, but the tech for contained fusion is only now emerging, and there are many difficult challenges. It's rocket science and nuclear physics, so you know, hard. But fusion turns less than 1 of rest mass into energy. What if we could get close to 100? Well, that's the idea behind option 3, antimatter drives. When matter meets its antimatter counterpart, both particles are annihilated, liberating most of the rest mass as energy. This is an extremely efficient fuel. For example, It would only take around 10 grams of antimatter to fly us to Mars in a month. The big obstacle here is that harvesting and storing antimatter is incredibly difficult. We can make in particle accelerators, but it's slow and hellishly expensive. We've only been able to do this with small numbers of antiprotons at a time, not the kilograms we'd need to get to the stars. Assuming we can scale up production of antiprotons by a factor of say 100 trillion, then pion rockets may be a possibility. Annihilate a proton and an antiproton, and you get charged pions moving at near light speed. Channeled with magnetic fields, these pions provide our thrust. That's something like 50 times more energy per kilogram of fuel than the best fusion options. Low fuel weight means our max speed is limited only by how much antimatter we can make. So, 5ek is plausible, meaning a trip to Alpha Cen would take 9 years. It may even be possible to push 0.8, which would be nice, because then time dilation really kicks in, bringing travel time down to 3 years from the astronaut's perspective. Rockets are cool and all. But what if we didn't have to carry any propellant at all? What if we could sail to the stars on a wind made of light, the light sail? I'm talking about a kilometer-wide sapphire-coated sail, riding the beam of a gigantic space laser blasting the power equivalent of 100 nuclear plants. What the hell? Let's do that. Most of the interstellar thinking for light sails has been about unmanned probes. 10 light speed is pretty reasonable with modern materials like a carbon web sail driven by a microwave beam running on a single nuclear power plant. This is an update to Robert Forward's Star-Wisp spacecraft, but it should be scalable. If we want to take actual humans, we're going to need a bigger boat, which means a proper visible light laser and a larger sail, coated with advanced, reflective and heat-resistant materials like sapphire. This laser is going to have to be ridiculously large, possibly built on the moon and powered by massive helium-3 reactors or in orbit around the sun powered by vast solar panels. How fast does this thing go? Because we aren't carrying any fuel, maximum speed is only limited by the power and collimation of our laser and the size of our sail. The longer the effective range of the beam, the higher the speed we can reach. 10 light speed or higher should be doable. These tech issues need to be factored into the weight calculation. And besides these, slowing down at the other end is a major problem. There are possibilities for breaking in the stellar wind of our destination star, although that is tricky. Ultimately, though, the scalability of the light sail means that speeds even greater than WEC are possible. Most awesome option for last, the black hole drive, in fact, a Schwarzschild Kugelblitz. This is an engine powered by an artificial black hole and is one of the fastest options for subliminal travel. This is a black hole made not from mass, but from light. A sufficient energy density of laser light focused in a small enough region would bend the fabric of space-time enough to produce a singularity, the Kugelblitz, German for ball lightning. A black hole of the right size radiates Hawking radiation like crazy. The smaller the black hole, the more radiation, and this radiation could drive our starship. The sweet spot is a black hole of around 600 billion kilograms or 2 Empire State Buildings, which would be roughly the size of a single proton. Such a black hole would radiate nearly 160 petawatts, which is roughly the equivalent of 10,000 times the world power consumption. And it would evaporate in around 3.1 years. Any smaller and it evaporates too quickly. Larger and it radiates too weakly and becomes too massive to feasibly accelerate the ship and the black hole. Assuming we can catch most of the radiation, this amount of power accelerates us to 1 in 20 days and presumably to a significant fraction of the speed of light in the lifespan of the black hole. There's no question that it ultimately goes faster than the other options. It's also clearly the coolest of all the subluminal engines. I mean, even the Romulans use it. The only drawback is that the lasers creating the black hole would need to be vastly more powerful than even the black hole they created. This is a possible yet very distant technology. So lots of ways to get to the stars. What's the fastest? Honestly, if we had to colonize in the absolute shortest possible time, then it's nukes, like the Orion project. We have the tech. We just have to increase the world's nuclear arsenal by a factor of 200, which we shouldn't do unless it's a question of extinction. Still, in a super optimistic estimate, we could have boots on the ground in 2120 or so. Now fusion engines are more sustainable, even if the tech is a minimum of 50 years away. They land us on Alpha Cen in the latter half of the 2100s, assuming we start now. Pure antimatter and the Kugelblitz drives. They're the starships of the far future. Assuming warp drives don't pan out, these are what will want to actually explore the galaxy with near-light speeds dilating apparent travel time down to human scales. Let's talk near-term reality. I'm going to come out and say it. Light sails. We'll put our first unmanned probes in the Alpha N system. It'll take around 45 years from launch, not slowing down at the other end, and another 4.5 years to get the message that we succeeded. Maybe we could launch a Star Wisp in less than 30 years, and some kids watching this video might see this to fruition. Manned light jammers are way off, but totally plausible. Humanity's first attempts to land on other worlds might well have us sailing to the stars. It's likely between this and post-fusion drives. Either way, pretty epic. Which option are you most excited about? Let us know in the comments. We hit Warp 7 next time on Space Time. Last week we talked about why the speed of light is really the speed of causality. You guys had lots of amazing questions. Andrea Propone and others asked, why does the speed of light have to be that specific number, 300,000 kilometers per second? And what would happen to the universe if it were different? Well, that actual number, 300,000 kilometers per second, just comes from a pretty arbitrary definition of the length of kilometers and seconds. Now physicists often choose to define the speed of light as c=1, which we call natural units. At that point, it perhaps becomes more interesting to ask why other fundamental constants of nature have the values that they do compared to the speed of light. Now that said, the relative units of the fundamental constants, the speed of light, the strength of the fundamental forces, etc. are important for the properties of this universe. And you change them too much, and the universe as we know it doesn't exist. We'll talk about that, and more in another episode. Jai Kolra and others ask, what about quantum entanglement? Shouldn't we be able to transmit messages instantly this way? Right. Spooky action at a distance, as Einstein called it, on the surface does seem to mess with us. When you collapse the wave function of one entangled particle, your choice of measurement affects the state of its entangled partner instantaneously, potentially over large distances. However, it turns out that this can't ever be used to transmit new information faster than the speed of light, so causality is preserved. We may do an episode on this, but in the meantime, Veritasium has us an excellent one, linked in the description. But Stefan asks why we're even talking about gravitational waves when none have ever been observed. Why don't we get back to this next week? But in the meantime, in pointing out the indirect detection of gravitational waves, Gareth Den delivers the amazing quote, so we haven't seen a duck, but something's been quacking and eating all of our breadsticks. Thekelanal asks, does this now mean I can refer to the speed of light as total monkey speed? The answer is yes. And to Tyler Hamilton, all I have to say is, yeah.